Hello, welcome to the lecture on Nyquist Plot. In this lecture, we will be dealing with the basics behind on how to plot a Nyquist plot and what will be the shape of the Nyquist plot and what will be the relation between the open loop transfer function and the closed loop transfer function. Welcome to the lecture. As an introduction, here in Nyquist plot we will be relating the location of roots of the characteristic equation with the open loop frequency response of the system. Okay, we know what is the open loop frequency response? Your g of s h of s. Characteristic equation is your 1 plus g of s h of s, right? Why this 1 plus g of s h of s is very important? Because based on the characteristic equation only the closed loop system stability is determined. Okay, so let us take then open loop transfer function g of s h of s. I am taking an example k into s plus 1 into s plus 2 divided by s plus 3 into s plus 4, right? This is an open loop g of s into h of s. In this I am going to plot this in s plane. What is s? Is sigma plus j omega. Then I am taking the characteristic equation that is given as qs. Qs equal to 1 plus g of s into h of s. Now I am substituting the g of s h of s in the qs. I got this expression. Then I am finding out qs, right? This plane is called qs plane, right? Characteristic equation is plotted in the qs plane. In qs plane I take the x-axis u and y-axis as jv, right? So throughout this lecture, throughout the Nyquist plot, we will be plotting from s plane to qs plane, right? In s plane the x-axis is sigma, the imaginary axis or y-axis is your j omega. In qs plane the x-axis or real axis is u and the y-axis or imaginary axis is jv, right? We will be seeing those things in the next few minutes. Okay, right. Now what I have done is I have brought the q of s here, right? As and see, this is s plus 3. What I have did is 1 plus q of s, 1 plus g into h. I got this expression, right? Now generally I am going to write, that is, on solving this I would be getting like s plus a into s plus b. Generally I am writing, right? I didn't give any values for a and b. So these are the zeros of q of s. Then s plus 3 and s plus 4. These are the poles of q of s, right? Is my q of s. Okay, now here I have written the open loop transfer function from the previous slide. Now we observe this. What are the open loop zeros? S is equal to minus 1, s is equal to minus 2. What are the open loop poles? I equate the denominator equal to 0, thereby I get s is equal to minus 3, s is equal to minus 4. These are my open loop poles, open loop zeros and open loop poles. Now here I am equating the numerator is equal to 0. I get the zeros of q of s, that is my s is equal to minus a, s is equal to minus b. Then if I equate q of s, denominator is equal to 0, I get s is equal to minus 3, s is equal to minus 4. Okay, right. Now if I equate, so now we understand the relation between these two, g of s and q of s. The relation is the open loop poles are same as the poles of q of s. This is the first point I want to stress here, right? The open loop poles of g of gh, open loop poles of gh is equal to poles of qs. First point. Next, what is if I equate it to 0, then that q of s I equate it to 0, it becomes a characteristic equation, right? I know what is q of s. I equate it to 0, denominator goes to the right side, it vanishes. So s plus a into s plus b, right? Now you equate s plus a and s plus b. The roots are s equal to minus a and s equal to minus b. So these are the roots of the characteristic equation. So roots of the characteristic equation are the zeros of q of s. Okay, this is the second point I want to stress here, right? First point is open loop poles or open loop poles of gh is equal to poles of q of s. Second point, roots of the characteristic equation is equal to zeros of q of s. Okay, fine. Okay, now we know that for the system to be stable, the roots of the characteristic equation and hence the zeros of q of s, these both are same. No, just now I have said, right? what I said, the roots of the characteristic equation and are is equal to zeros of q of s must lie in the left half of the s plane, right? And inclusive of, and we can say this point left half, but I can allow if there is a single pole at the origin, that is permitted, right? Okay, all the poles should be in the left half, but a single pole at the origin is also permitted. Okay. But the pole should not repeat. Okay, like 1 by s square is unstable, right? But 1 by s is stable, keep in mind. Okay, must lie in the left half of the s plane inclusive of, this is s, right? S plane inclusive of non-repeating poles at the origin. Okay, now generally I am taking like a generic expression like q of s. What is q of s? Yes, q of s is 1 plus gh. On solving that, I get s minus alpha 1 s minus alpha 2 divided by s minus beta 1 divided by into s minus beta 2. Okay, so alpha 1 alpha 2 are the zeros of q of s, beta 1 beta 2 are the poles of q of s. Now what I am going to do is, I said already, s is a complex variable sigma plus j omega. Q of s is also a complex, but it is defined by real part is u plus j imaginary part jv. I am going to map from s plane to qs plane. Okay, what I am doing is, look at the highlighter I am pointing here, right? Okay, I am moving in what direction? I am moving in the clockwise direction. So assume I am walking this way, right? I am walking in this line, right? Where my right hand will be? Right hand will be inside, pointing inside, right? I am walking in this line, my right hand will be pointing inwards, right? Inwards, right? Okay, so this is the region I am enclosing, right? So this red line encloses this region. I am assuming some points s1, s2, s3. These are the points in what plane? S plane. In S plane, the real axis is sigma, imaginary axis is j omega. Now, for each point in S plane, there would be a corresponding point in, I am putting S some value here, right? S, let me say S is some value. Let this point is 2 plus j1. This point is 3 plus j2. This point is 4 plus j1. Right? I put some values of S. Definitely, this would be an imaginary. So I equate the real part is u, imaginary part is v. There will be a corresponding point in the qs plane. So if I put s1, that corresponding point is qs1. If I put s2, the corresponding point is qs2. If I put s3, the corresponding point is qs3. So this is one-to-one point mapping. Okay, this idea is very essential, right? So from the S plane, I am going to corresponding points are mapped in the qs plane. And also you should ensure that which is the region enclosed, right? Since I am moving in clockwise direction, the inside region is the enclosed region. Fine. Now one more thing, the path I am walking now in this red line that I am highlighting, that should not have any poles, right? The mathematical reason you will be learning in complex integration, right? They should not have any poles. Okay. The path should not have any poles. Okay, now let me say q of s is there, and see in this q of s, it is in what form? If I put j omega or some values of s I am putting, it will be in Cartesian form or rectangular form, real part plus imaginary part. I am going to express that in polar form. So I am taking the magnitude of each term, phase angle of each term. Since for the denominator I am putting in the negative. Now look what is there. I am taking an example plot in the S plane. Okay, how many poles are there? 1, 2, 3, beta 1, beta 2, beta 3, 3 poles are there. How many zeros are there? Alpha 1, alpha 2, alpha 3. Out of these 3 poles and 3 zeros, only alpha 1 is enclosed by this contour. Contour is nothing but a closed path. Okay, I am walking in what direction? Clockwise direction. So alpha 1 is enclosed inside the contour, red line. Okay, fine. Now look at the contribution of the phase angle of the terms, right? What is the phase angle contributed by the beta 1 over this contour? Let's look here, beta 1. I am putting a phase straight line here, right? So what happens when I am moving? The angle increases, angle again decreases. Okay, so the net angle is 0. Net angle is 0 for this phase or the net angle is again 0. For this phasor, net angle is again 0. For the alpha 2, the net angle is 0. For beta 3, net angle contributed towards this contour is 0. But for this alpha 1, okay, which is inside the contour, look at the phase angle contribution. See, its phasor line is going, right? I am walking in what direction? Clockwise direction, right? I am moving. So total angle contributed by the phasor is in the clockwise direction. I am moving 360 degree. Clockwise means angle is negative, no? So it is minus 2 pi. So 0, that is your alpha 1, goes through a total angle of minus 2 pi. Okay. So what I am doing is, this point is very important, right? Like, see, this is S plane, this is QS plane. So U, JV for QS plane. So because of 1, 0 enclosed by the contour, this is going to encircle the origin. Okay, we know in polar form what we represent, we take the magnitude and phase angle, right? Since because of 0, the total phase angle is minus 2 pi or minus 360 degree. Minus 360 means clockwise direction. Look, the arrow I have marked is in clockwise direction. So origin is enclosed. See, phasor we always we take from the origin, right? Origin, right? This is a phasor. This line is a phasor magnitude. Angle is your angle of QS, right? Since it is coming as minus 2 pi, the angle would be a complete circle in the clockwise direction. Okay. Remember, the shape I have drawn here is not important for us. Only the angle contributed is important, right? We will understand these things in the next few slides. Why the shape? Why we are not worried about the shape? We are interested only in the phase angle. Determine the stability. We are interested only in the phase angle. We are not worried about the magnitudes, right? Okay. Now, look at the second example. Yes. In second example, two zeros are enclosed, right? The zeros are alpha 1 and alpha 2. Already we have seen for a single alpha, the total phase angle contribution is minus 2 pi. For 2 alpha, it is minus 4 pi. Minus 4 pi is nothing but minus 720 degree. So, origin is enclosed in clockwise direction twice. See, this is a clockwise direction, no? So, first circle, second circle, right? So, if you look at the origin, this is first circle, this is the second circle. 2 times it is enclosed. So, simply remember the concept. If 1 0 is enclosed, it is going to revolve the origin twice. Going to revolve the origin twice in clockwise direction. Okay, right? It encircles the origin once with an angle in clockwise direction. It encircles the origin twice in the clockwise direction. Okay, the angle should be like angle minus 2 pi. Twice means minus 4 pi. For clockwise, I put the minus sign, right? That's important. Okay. Now, okay. Look at this example now. Third one. In third one, there are two poles are enclosed by this contour, right? I have said that for a 0, the angle is minus 2 pi, right? For the pole, the angle is still minus 2 pi. It's accepted. But look at this expression, right? What happens? The numerator angles are the, for the numerator term, angles are positive. For the denominator term, that is the for poles, the angles are negative. So, if this is minus 2 pi, minus minus becomes plus. So, for each pole, the angle contribution is 2 pi. Since two poles are enclosed, the angle contribution is 4 pi. So, origin is enclosed. This is in 2 pi means anti-clockwise direction, right? Positive degree is in anti-clockwise. Clockwise means negative degree, right? Anti-clockwise means positive degree. Okay. So, since it is in anti-clockwise against the clock direction, see clock direction against, so this is 2 pi degree, then this is another 2 pi degree. Okay. That is what is mentioned here. It encircles the origin twice in the counterclockwise. Counterclockwise I can say or clockwise I can say. Now look at the last one. See how many poles are there? 1, 2, 3. How many zeros are there? 2 zeros are there, right? So each zeros will contribute an angle of minus 2 pi. Each pole will contribute an angle of plus 2 pi. So zeros and pole will get cancelled. What is remaining? One pole is extra. Each pole we know the angle is 2 pi. 2 pi means what is the direction? Counterclockwise direction. That is why it is encircling the origin once. Okay, 2 poles, 2 zeros, 3 poles. So the net encirclement is 2 pi. Okay, remember this concept of mapping is based on the theory of complex variables. Due to Cauchy is called principle of argument. In maths, in complex, I can't what's the topic is like complex integration. In those things you'll be learning these things, right? Those topics will be covering these ideas. So this sort of mapping is called principle of argument from S plane to QS plane. Okay, this is your S plane. S plane, this is your QS plane, right? That's what I say here. Each enclosed zero contribute minus 2 pi. Minus 2 pi means clockwise encirclement in the QS plane. Each enclosed pole contributes 2 pi in anti-clockwise direction. It's the encirclement in the QS plane. Okay. Now we are going to investigate whether investigate the presence of any zeros of Q of S, right? Why this is very important for me? Why I am investigating the zeros of Q of S? Because zeros of Q of S is nothing but roots of the characteristic equation, right? We have seen already. We have seen here. Right? Roots of the characteristic equation is minus a minus b are nothing but zeros of Q of S. For this also minus a minus b. Okay. Right? In order to investigate the presence of any zeros of Q of S, in the right half of the S plane, we choose a contour which is completely encloses the right half of the S plane, right? So I am taking the S plane, right? In this, I am going to cover the entire right half. Entire right half is this region. For this, I am going to take a contour. Contour is nothing but a closed path. Okay. So for that, what I have to do? For this contour C is called Nyquist contour. Okay. It is directed along the clockwise direction. See, the contour is in what direction? Clockwise direction. How many segments are there? 2 segments. The straight line. Straight line I give the name C1. This semicircle I give the name C2. Right? The straight line is going, it should cover the entire right side. So it should go from minus infinite to plus infinite. So minus j infinite to plus j infinite. So C1 is equal to Sj omega, where omega equal to minus infinite to plus infinite. So this will cover this entire line. Next, come to the segment C2. Okay, C2, what is C2? It's an infinite semicircular arc. It's an infinite, very large arc, but it is semicircle, right? Only one side, one half. So what I do is R equal to e power minus j5. This R is your magnitude or radius of the circle, where angle phi is from this line, you know, this is 0 degree. So this line is 90 degree. Okay, this line is 0 degree, this line is minus 90 degree. So I will be changing the phi from 90 to 0 degree, then to minus 90 degree. So R e power j5. R is the radius of the circle or semicircle is going to be infinite. So this radius is a very large radius such that it covers the entire right side of the S plane. Okay, that's why I make R as infinite, and phi is to be from angle phi is from, for this line it is 90, for this line 0 degree, for this line it is minus 90 degree. This Nyquist contour encloses all the right half of the S plane. Okay, this is very simple. Keep in mind this imaginary axis is by j omega. Omega is from minus infinite to plus infinite. This entire right side is brought by the infinite semicircular arc. So for infinite I make R as infinite. For phi is from this line is 90 to 0 degree to minus 90 degree. Thereby I cover the entire right side using the segments C1 and C2. And very important point to be noted is there should not be any poles on the contour lines, right? On these lines C1 and C2 should not have any poles. Okay, A problem having like I can say if there is a pole at the origin, we should have a different approach. Those concepts I will explain in the next video lecture, right? Okay, we have first take a simple case, right? But these sort of problems itself quite complicated, right? Those things we'll see in the next lecture. Let's wait for some time. Okay, right. What is Nyquist contour? Nyquist contour is defined such that it encloses the entire right half of the S-plane. Okay, let us assume that for Q of S, what is Q of S? 1 plus GH have Z zeros and P poles in the right half of the S-plane. We are assuming that Q of S is having Z zeros and Q poles, P poles, right? Z zeros and P poles in the right half of the S-plane. So correspondingly, see, that's important, right? Not all poles we are taking. What are the poles and what are the zeros in Q of S in the right half of the S-plane we are considering. Okay. So in correspondingly, in the QS plane, it encloses the origin n times in the counterclockwise direction. Okay. Because we know poles contribute what angle? Poles contribute the positive angle. Each pole will contribute, each encircled pole or each enclosed pole will contribute angle 2 pi. Each 2 pi in the sense positive angle, that is in the counterclockwise direction. Zeros will contribute in the minus 2 pi. Each enclosed zero will contribute an angle minus 2 pi. Okay, here what you are doing is you are taking QS. In the QS, if it is having Z zeros and Z poles in the right half of the S plane, so what we are going to do is in the QS plane, what is going to happen is it encloses the origin n times in counterclockwise direction, where n is equal to P minus Z, where P is the poles of Q of S in the right half of the S plane, where Z is the poles zeros of Q of S in the right half of the S plane. Okay, now very important, for the system to be stable, what is the condition? Here the system to be stable means closed loop system. Okay, for the closed loop system to be stable, characteristic equation should not have poles in the right side. Okay, what is characteristic equation? Characteristic equation nothing but the zeros of Q of S. Okay, so for a stable system, Q of S should not have zeros in the right half of the S plane, that is 0 should not be there in the right side, so n is equal to P. Next, for a open loop stable system, that is no poles in the right side of the S plane. Okay, in that case P is equal to 0, right? We know for the open loop poles is equal to the poles of Q of S. I have stressed that point 1 and point 2 in the very beginning of the lecture, right? Okay, so for the open loop stable system, P is equal to 0. So for the closed loop system to be stable, that is n and P is equal to 0, no encirclement of the origin, right? Okay, now very important. See, I want to refresh these things again. Okay, if the Q of S is having Z zeros and P poles on the right half of the S plane, then in the QS plane it will encircle the origin n times in the counterclockwise direction, where n is given as P minus Z. Simple. If the system is stable, we know for the stable system Z is 0. What is Z? Roots of the characteristic equation are the poles of or the zeros of Q of S. Okay, so n is equal to P. For an open loop stable system means what? That is G of S, H of S. The poles, that is the denominator terms, should not lie in the right side. Okay, so what we can do? The closed loop, so that is equal to P. For that, in that case, n is equal to P. No encirclement of the origin in the QS plane. right? Now what is happening is, see, observe very closely. What is this term? 1 plus GH is your Q. If I subtract 1, what happens? That becomes your GH. Okay, so you have, until now we discussed the concept of Q of S, right? So if I can Q of S, if I know, if I subtract minus 1, that will become my G of H. Okay, so by indirectly indirectly studying about 1 plus GH, we can relate GH with 1 plus GH. Okay, this relation you can understand, right? In QS plane, what we did, look at the green lines. This green line is for 1 plus GH. 1 plus GH, right? What I did, 1 plus GH becomes GH. 1 plus GH is a characteristic equation. It's very important to determine the stability. Becomes GH when I subtract minus 1. So I am going to subtract minus 1. From the green, if I subtract minus 1, what happens? This point will come here. This point is coming 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 here. You can see, no, each point is moving. It is moving, right? So the blue line is nothing but your GH line. Okay, so until now we have said that it encircles the origin, n is equal to p minus z. Now we have shifted by minus 1. We have shifted by minus 1. So it becomes, so instead of origin, hereafter we are going to speak about minus 1 plus j 0. Okay, now if the contour g of s h of contour GH of the open loop function encircles the point, this is the Nyquist stability criterion, right? If the contour GH of the open loop transfer function encircles the point minus 1 plus J0 in the counterclockwise direction in the QS plane as many times as the number of right half S plane poles, then the closed loop system is stable. Okay, if you are, that's your this expression, just a moment, this expression. Okay, if we don't have any zeros in the right half of the S plane, then n becomes p. The same way, what we do, instead of origin, we are replacing with minus 1 plus j0. Okay, if we have only the poles, that in the right half of the S plane, it will encircle minus 1 plus j0 that many times in the counterclockwise direction. This is the Nyquist stability criterion, right? Suppose if the open loop system is stable, that is no poles on the right side of the S plane, then the contour does not encircle minus 1 plus j0 point. Okay, right? Again I read the statement. If the contour GH of the open loop transfer function encircles the point minus 1 plus j0 in the counterclockwise direction in the QS plane as many times as the number of right half S plane poles of G and H, then the closed loop system is stable. Okay, right? In the QS plane, if it is encircling some number of times, that is equal to number of open loop poles in the right side of the S plane, then I can say the system is stable. If that is not equal, then I say it is unstable. If you solve a problem, you get a very clear idea. Just a moment, wait please. Okay, first example we take. It's given, a open loop transfer function is given. Okay, they are asking draw the Nyquist plot and assess the stability of the closed loop system for the given open loop transfer function. Okay, what are the open loop transfer functions? Zeros are minus 4, poles are minus 1 and 1. So it's very clear, right? You observe closely. Now what I'm going to do is I am going to construct Q of S. Q of S is 1 plus GH. Okay, I am putting GH value, I got this expression, right? Now I am going to find out what is P. What is P? Poles of Q of S, number of open loop poles of, it should, yes, it should be like not open loop poles, beg your pardon, it should be poles. It's a number of poles of Q of S in the right half of the S plane. What are the poles? These are the poles. One pole is at minus 1, another pole is at plus 1. So one pole is in right side. So P is equal to 1. Okay. So what should be the Nyquist stability criterion? One pole is in right side. No. So it should encircle minus 1 plus j0 1 times in the counterclockwise direction for the system to be stable. stable. Very important statement, right? Based on this result, I'm going to frame the stability statement. Nyquist stability criterion states that the closed loop system is stable if the Nyquist plot of g of s h of s must encircle the point minus 1 plus j0 of qs plane once in the counterclockwise direction. Because p is 1, so it should encircle once in the counterclockwise direction, which point minus 1 plus j0. If it is not enclosing, then it is unstable. Okay, how to check this, enclosing or not? How to check this? I have to plot the Nyquist plot. From the Nyquist plot only I can check this condition. Okay, let's go into the Nyquist plot. Right, what I did is, in place of s I substituted j omega. I have to convert this from s plane to j omega, s to j omega. Then I have to split it into real part and imaginary part. Okay, so this is j omega plus 1, j omega minus 1. So I converted this into 1 minus j omega. I have taken minus 1 outside. So it becomes j omega minus 1 becomes 1 minus j omega, minus 1 I taken outside. So a minus b, a plus b. So I converted into a square plus b square format. Okay, right, I got this value. I have to split this into real and imaginary part. This is fundamental step. That is, this is your u, this is your v, jv, u plus jv. That plane is called qs plane. QS plane. In QS plane, what is the meaning? U plus JV format. Okay, right. We know I have to cover the entire right side in the S plane. So what I am doing is I am taking the segment C1. Segment C1, omega is from minus infinite to plus infinite. In minus infinite to plus infinite, I am going to take the points like say I am going from the minus infinite to plus infinite, means I go to minus infinite to 0, minus 0, then plus 0 to plus infinite. I am going to substitute various values of these values here. Okay, these are fundamentals, right? In omega, I am going to substitute minus omega, thereby I get the value minus 0 plus j0. Then in place of omega, I am substituting minus 0. Okay, if I substitute, I get minus 4 plus j0. Then plus 0, I am going to substitute minus 4 minus j0. In place of omega, I am substituting infinite. I get minus 0 minus j0. I got the 4 points. Okay, this is the points in the S plane. No, this is the for various values of omega. That's the points in the S plane. I am getting the points in the, these are the points in the QS plane. These are the U values, JV values, U values, JV values. Okay, right. Now I am going to the segment C2. In the segment C2, what is segment C2? It's a semicircular infinite arc. So I am going to put R as infinite, e power j phi. Angle phi is from 90, 0 degree and to minus 90 degree. So in place of s I substituted, transfer function is given as s plus 4 divided by s minus 1 into s plus 1. In place of s I substituted these values. This I think is in polar form. Okay, I said the R is infinite. So infinite plus 4, I can ignore the 4. Infinite minus 1, ignore the 1. Infinite minus plus 1, I ignore the plus 1. Okay, so this becomes, this 4 minus 1 plus 1 is gone. So these two terms get cancelled. So 1 by r e power j phi. Okay, so r I put infinite means what happens? It becomes 0. So e power j phi goes to the numerator. It becomes e power minus j phi. What is the angle of phi? Angle of phi is from minus 90, 0 degree, and plus 90, 0 degree and minus 90 degree. So because since r becomes 0, radius is 0, phi varies from, if I put it's from plus 90 minus 0 degree to minus 90 degree. Okay, just a moment. Okay, yes, it should not be like plus 90. It should be okay, this should be minus 90 plus 90, because you see I am going to put phi as 90. So already it's minus sign, so minus 90. Then if I put 0, it is 0. If I put minus 90, minus plus 90. So this is the angle. So I got the corresponding points for C1, segment C1, and the points for radius of 0 and the corresponding phase angles. Now I am going to plot. Okay, right. You observe this. This is my S plane. This is my C1 line segment. C1 is from minus infinite to minus 0, plus 0 to plus infinite. Then the C2 is nothing but R e power j5, where R tends to infinite. Now I plot the point. Look at very closely. But omega equal to minus infinite, point is minus 0 plus j0. At omega equal to plus infinite, the point is minus 0 minus j0. Okay, what should be the direction? Yes, the direction is always from, what is the angle range of omega? Omega, you see, this is the contour, right? I said the contour I am assuming is in clockwise direction. I am putting an arrow, please observe, right? It is in what direction? Clockwise direction. Then only it can encircle. Okay, it is encircling. Look here, it is encircling what? I have marked the pole 0 plot beautifully, right? There are two poles. One is at minus 1, another is at plus 1, another 0 is at minus 4. So it is encircling one pole. So that means it should encircle minus 1 plus j theta, minus 1 plus j0 once in the counterclockwise direction. Let's see whether it is doing that or not. Okay. For that, what I am doing is I am going from minus infinite. For minus infinite, corresponding point is this. So from minus infinite, I go to what point? 0 minus. For 0 minus, the point is minus 4 j0. Okay. Then I go into 0 plus. For 0 plus, the point is minus 4 j0. It's here. Then I go to plus j infinite. For that, the point corresponding is minus 0 minus j0. Okay, so it's obviously it is going in this way, because you can go in this way only, right? I have to go from minus infinite to 0 minus, then 0 plus to 0 infinite. That means it is encircling minus 1 plus j0 point once in what direction? Counterclockwise direction, right? Next thing, how at one point it is cutting the imaginary axis. Those points is required, right? For that, what we can do is we have to equate the real and imaginary part. This problem is quite obviously, I can say it is cutting the real axis at minus 4. It is not going to cut the imaginary axis. So this length is 4, right? So I can say, I said the condition for stability is it should encircle the minus 1 plus j0 point once in the counterclockwise direction. This is also encircling once. So from the plot, I can say from the plot, it encircling the point minus 1 plus j0 once in the counterclockwise direction. So the closed loop system is stable. That's the conclusion. Okay, right. Next problem. They are asking that they are given g of s, h of s, right? In this they are asking comment on stability. Okay, first thing, we have to find the number of open loop poles of q of s, right? What is q of s? What is q of s? Q of s is equal to 1 plus g h, that is 1 plus k into s minus 4 divided by s plus 1 square, that is s plus 1 square plus k into s minus 4 divided by s plus 1 square. Okay, so observe very closely the statement I have given here. This is your poles of q of s, right? Poles of q of s is nothing, again I have repeated is just to make point clear for you, right? Poles of q of s is nothing but the poles of g of s, gh, right? So poles of gh is minus 1, both are in the left side, none is in the right side. Okay, that means number of open loop poles in the right side of the s plane is 0, so p is equal to 0. That means your Nyquist plot should not encircle, for the stable system should not encircle minus 1 plus j0. We will see whether it is encircling or not. Okay, so what I do is gh is given, in place of s I substitute a j omega. Okay, in the denominator it's a complex function, so what I have to do is I have to take the complex conjugate. So 1 plus j omega, the conjugate is 1 minus j omega, so I divide and multiply by 1 minus j omega whole square. Okay, so it becomes like now the denominator becomes a real part, right? 1 plus omega square whole square. Then I have to expand this, multiply, you will get this real part plus j into imaginary part. This you please work it out, right? Simple max only, just work it out, splitting into real part and imaginary part. Now for the segment C1, what I do is I start from omega, as we discussed already, omega minus infinite, omega 0, omega plus 0, omega plus infinite. I will be finding out the corresponding points in QS plane, right? When I put omega minus infinite, I get the g j omega h j omega as 0 plus j omega. When I put omega as minus 0, I get minus 4k minus j0. When I put plus 0, minus 4k plus j0. When I put omega as infinite, I get 0 minus j0. You please work out these values. They are very simple things, right? Okay. For the S plane to corresponding QS plane, I got those 4 points. Okay. For the segment C1. Next. Here I am going to take the segment C2, which is an infinite semicircular arc, right? For an infinite semicircular arc, what is the condition? Limit r tends to infinite, r into e power j phi, where angle r is going to be infinite, that is going to cover the entire S plane in the right side, and the angle is from plus 90 to 0 degree to minus 90 degree. In place of s, I have substituted this value. In the question, it is k into s minus 4 divided by s plus 1 whole square. In place of s, I am working with polar form, so straight away I substituted these values. Okay, so since r is an infinite value, minus 4, I can ignore the 4. Since r is infinite, I can ignore the 1. Okay, so r e power j phi divided by r e power j phi whole square. So one of the terms r e power j phi will get cancelled out. So k, I have this r e power j phi. So since r is infinite, so look at the limit is here, r is infinite, 1 by infinite is 0. So k by infinite is 0. So e power j phi goes to the numerator. So it becomes e power minus j phi. I know the range of phi. The phi is from 90 degree. Since minus sign is there, so minus 90 degree. Then it goes to 0 degree. So if I put plus 90, if I put minus 90, I go to plus 90. So this is the range of segment C2. The radius is 0. But the phase angle is from minus 90, 0, plus 90, right? Now, I have written again the I have split it g of j omega to j omega. I have written again, right? Because I need to find where it is cutting the imaginary and real axis. Okay. For that I have written. Before that, we will try to plot the points. Okay, we go to the next slide. So look what I am doing here. At omega equal to minus infinite, the point is 0 plus j0. Okay. Just a moment. This should be plus infinite, sorry. This should be plus infinite, right? So omega minus infinite, I get 0 plus j0. Then omega 0 plus, the point is minus 4k plus j0. Omega 0 minus 4k, this is the point, minus 4k minus j0, right? And for omega plus infinite it is 0 minus j0, right? Understand the difference between 0 minus j0 and 0 plus j0. 0 plus j0 is slightly above 0 or very close to 0 in this direction. 0 minus j0 is slightly below 0 in this direction. Minus j0 is this, right? So minus 4 plus j0 is this direction here, very close to 0. Minus 4k minus j0 is here, right? This is slightly above the real axis, this is slightly below the real axis. Okay. Now we got the 4 points, but still we have to identify where this plot is going to cut the imaginary axis, right? Real axis and imaginary axis. Okay. For that, what I did is I'm going to use this expression. We know to find the imaginary axis point intersection, I have to equate the real part. To cut the imaginary axis, if you are cutting the imaginary axis, what is the meaning? Real part is 0. So I equate the real part is equal to 0. I got omega as square root of 2 by 3. This is the omega. Okay, right? So I take this omega, put it in the expression. If I put it in the expression, if I put 2 by 3, this becomes 0. I get solving this. Okay, on solving this, I get omega as 2.45. So at omega equal to square root of 2 by 3, the point is, this point is j 2.45. Then what is the meaning? Omega is of two values? No. So omega equal to minus square root of 2 by 3, I would be getting, this point is minus j 2.45. Okay. Now let us try point where it cuts the real axis. To find the point in the real axis, what I should do? Real axis means imaginary part is 0. No, imaginary part is 0. So equate this term to 0. That's what I did here. Equating this term to 0, I get omega as plus or minus 3. Right? So if I put plus or minus 3, plus or minus 3, what happens? Put plus or minus 3, this term becomes 0 for plus 3 or minus 3. So I put it here. On solving this, I get this as k by 2. Okay, substitute omega equal to 3 in this term. I will get k as, this term as k by 2. Okay. So at omega equal to 3 or omega equal to minus 3, this term becomes k by 2. Right. Now you observe, we are starting at what point? That this term, this is from minus infinite to 0 to 0 plus j 0 plus to j infinite to some values. Okay. Omega equal to, see, omega equal to infinite to negative of 0 to plus of 0, omega to plus infinite to other values you are moving. So here you look here, we are at minus infinite. Okay. So what you have to do? From minus infinite, I have to go to 0. In between, I have the minus 3, the point is k by 2. So my Nyquist plot should be in this direction. Okay, right. Next, I have to go to 0 minus. Where is 0 minus? Is here. So minus infinite to omega minus 3, I go to, this point is minus square root of 2 by 3. I go to this value. Then plus 0, 3 is here, I come to plus infinite. Okay, this is the Nyquist plot. Always remember, Nyquist plot is symmetry about the real axis, right? Whatever here, it comes in the mirror image this way, right? Okay. So again, the shape is, some people will ask, sir, why you are going in this way? Why I can't go this way like this? You can go, nothing wrong. Only thing, whether we are encircling, the objective is whether we are encircling or not. That is our objective. Okay, right. By looking at this, it seems that we are encircling. But observe very closely, the encircling value depends on this. This point is minus 1 plus j0. Here we have minus 4k. Based on k only, if I put k as 0, this point will come here, right? If I put k as 1, this point is minus 4. If I put k as minus 0.1, if I put k as 0.1, what happens? 0.1 means 4 into 0.1 minus 0.4. It will come here. Okay, in that case, do not encircle this value. So range of k only determines the stability. Okay, how to determine the range of k? We can get the help from the Routh table, right? So g of s, h of s, we construct the characteristic equation. We form the characteristic equation, right? Go for the Routh table. 2 plus k, 1 minus 4k. 2 plus k should be positive, so k should be greater than minus 2. 1 minus 4k should be positive, so k should be less than 1 by 4. So if the k is between minus 2 and 1 by 4, the system is stable, right? Okay. So when the k is between minus 2 and 1 by 4, okay, you take any value. Let me say k is 0. When I put k 0, what happened? This point comes here, so it will not encircle. there won't be any encirclement. Any encirclements, n is equal to 0. Already we know what is p. P is also equal to 0, so z equal to 0. That is, no zeros of q of s lies in the right side of the s plane. Zeros of q of s is nothing but the characteristic equation. So the system is stable for this range of k. Next, if for the k, if the k is less than minus 1 by 2 or k is greater than 1 by 4, okay, other than which we are disobeying this condition, in that case it becomes unstable, right? Okay, when it becomes unstable, it will be encircling once, that is your n minus p minus z. We know already p is equal to 0. From the plot for under this condition, from the plot with this condition, right, it encircles minus 1 plus j0 once in the clockwise direction. So n is equal to, see p is 0, so z is n is equal to minus 1. One time it's encircling, but it is not in counterclockwise direction. It is in the clockwise direction. So we are putting n as minus 1. Remember, in counterclockwise direction means we will put 1. This is encircling in the clockwise direction. So we are putting minus 1. So minus 1 is equal to 0 minus z. So z equal to 1. Z equal to 1 means one of the zeros of q of s is right side of the s plane. If one of the zeros means roots of the characteristic equation 1 is in the right side, so the system is unstable. Okay, I hope this already 51 minutes, right? I hope you learned something from this lecture. Okay, please listen it again. Here the simple thing, we are using principle of argument. We are going to plot from GH plane to 1 plus GH plane, that is S plane to QS plane. For that, to cover the right side, we are taking a segment C1 for the imaginary axis. For the entire right side, we are taking a segment C2 whose radius is R, and to cover the angle, I am going from angle phi from 90 degree to 0 degree and minus 90 degree. Okay, for that for me the shape is not important, only the number of encirclement is important. Right? If it is having n is equal to p minus z, p is the poles of q of s, z is the zeros of q of s in the right side of the s plane. Okay, that means for system to be stable, n times encirclement of minus 1 plus j0 in the counterclockwise direction should happen. Then only the system is stable. Okay, right. Thanks for listening. Any doubts, please post in the comment section. Okay, I have referred Ananda Kumar book, right? You can refer that book also. That will be helpful. Please listen to the lecture. Pause, take notes, then listen. You can understand well. Thanks for listening. Happy learning.